All right, so let's talk concavity. There's going to be two types of concavity. There's going to be concave up, like a happy face, and there's going to be concave down, like a sad face. And that's one of the things that in pre-cal we weren't able to really prove that we had concave up or concave down. We just said that, okay, this looks like it's concave up, this looks like it's concave down. We could say something about the secant lines. Anyways, so we'll look at concavity, and what I'm going to do is I'm going to draw a couple of my tangent lines. So this first one has a negative slope, and then probably a horizontal slope, or slope of 0, and then a positive slope, so that you see that it is increasing. So the slopes of those tangent lines are increasing, and slopes of the tangent lines are the first derivative at those points. So we say if f prime, the first derivative, is increasing, then we have concave up. Okay. Also, if we draw any secant lines, the secant lines will appear above the graph. Okay, and then we'll do something that's concave down, and we'll draw a couple of tangent lines, and you'll notice that we have positive slope, probably 0 slope, and then negative slope, so the slope of the tangent lines is decreasing, so that means our first derivative is decreasing. Oops. F prime is decreasing, so we have concave down, and our secant lines would appear under the graph, or below the graph. Okay, so there you go. There's your happy and your sad face for concave up and concave down. Okay, so what we're going to look at here is if the second derivative exists on an open interval I, if for all x the second derivative is positive, that means the first derivative is increasing, and we just said that means first derivative is increasing, we have concave up. Okay. If for all x in the interval the second derivative is negative, that means the first derivative is decreasing, and if it was decreasing, then we have concave down. On that interval I. Okay. So what we're going to test for concavity is we're going to look around where the second derivative is 0, and then we will also explore where the function might be undefined, because there might be asymptotes, and asymptotes may be of interest. There may be some changes in concavity there. All right. So let's do an example. We'll find all intervals of concave up and concave down. So let's see, we'll say f of x is equal to x cubed minus 4x squared. This is a nice differentiable function, so the second derivative is going to exist everywhere. Polynomials are differentiable infinitely many times, so we can take the derivative as many times as we like. I'm going to take that first derivative. I'm going to use the power rule. 3x squared minus 8x. We'll take that second derivative. We get 6x minus 8. And then we're interested in when the second derivative is equal to 0, because that's when we may have some change in concavity. And if we solve that, x will be equal to 4/3, and then we can make ourselves a little number line just to test around 4/3. So f double prime of, for instance, 0 is going to give us -8, so we'll have concave down. F double prime of 2 will be 4, so we're going to have concave up. And you see that we changed concavity from concave down to concave up. If we change concavity, then we call that a point of inflection. So our point of inflection here is 4/3. And then we'll have to plug it into the original function. So I'll leave that to the viewer to figure that out. Now I don't believe this is the correct graph, so I think I end up erasing this, so I made a boo-boo on this. Alright, so let's graph the correct graph. Okay, so x-intercept at 4 and 0. So it looks something like that. And I have a point of inflection somewhere in this region here. So we see that we have the sad face all the way up to this point of inflection, and then we change from concave up to, or concave down to concave up. And there's some applications, where you might have a point of inflection that might be like a point of diminishing returns. All right, now let's do another example. We'll look at, what do we got here? Okay, so we're going to look at the reciprocal function. So we'll take the derivative, and then we'll take the derivative again, and so there's what it looks like. It's only undefined at x equals 0, so we're going to kind of check out what's going around 0. So we'll test to the left, and we'll test to the right, and we'll find concave down on the left and concave up on the right. And you might say, oh, well, isn't 0 the point of inflection? And I would say, oh, I'm sorry, it's not, because 0 is not defined. No divided by 0, so it's not a point of inflection. It has to be defined for the function. All right, and here's our reciprocal function. So there's the sad face, there's the happy face for our concave down and our concave up. Okay, let's do one more example. I think we'll do something a little bit more exciting. What do we got here? X squared plus 1 to the 1/2 power. Ooh, that's a good one. So we're going to have to use the chain rule. So 1/2 comes down, x squared plus 1, subtract 1 from your exponent, minus 1/2, and then the derivative of the inside, which is 2x. Okay, so the 2 and the 1/2 cancel each other out. We're going to pull the x out to the front and just rewrite. Okay, and then we're going to take the second derivative. So we're going to to take the second derivative, we got a product here, don't we? Yeah, we got a product. So we're going to take the derivative first, and then times the second function. And then the first function times the derivative of the second, so that minus 1/2 comes down, times the first function, which is the x. Subtract 1 from your exponent, and then times the derivative of the inside. Okay, then your favorite part is factoring out the smallest exponent, which is the 3/2. So when I remove that, I'll be left with an x squared plus 1 and an x squared. So the 1/2 and the 2 take each other out. So after all that hard work, we have 1 over x squared plus 1 to the 3/2. And that's positive all the time. It's positive over positive, so that's positive for all real numbers. So it is concave up all the time. This is a happy function. Concave up all the time.